In this segment, I want to start working with geospatial data inside SQL Server. So we uploaded the world countries dataset, and we uploaded the US states from the Census Bureau, in addition to the counties and zip codes. In my SQL Server 2019, I have loaded some additional data that I will be covering. So I just want to show that to you now. One is a data set that has to do with fast food restaurants, and one is for Target stores, which is a chain here in the US. And also I uploaded into a table the world airports data set. And as you can see here, the links to where you can go to download this. So very quickly, let me show you what it looks like. This is the fast food from the ArcGIS Hub. You can download this data set. And as you can see, it has ID, address, city, state, zip, phone. It's so lat and long. And there's a restaurant, whatever state is in it, and so forth. The second data set is this Target store data set that looks something like this. You can download this Target's CSV file from Kaggle. The third one is this airport data set. And you can basically go to GitHub here and get a CSV file and download that data set. Once you download that, you can upload it into SQL Server. And when you do, you can create tables that look something like this. So here is the world airports. So if I run a quick select on that, you can see this is what it will look like. So this particular field will have the 3-letter code for an airport. For example, O'Hare Airport here in Chicago will have ORD. So it has a latitude, a longitude, and some additional fields here. I also created, as part of this data set, a geography column that I built from this latitude, longitude data set. I think that's what I did. Let me see quickly here. Yeah, you can see all the points here that's showing up on the grid. The second data set that I was mentioning is these Target data stores. And once you upload that, it has a lot of fields. Obviously, you're not going to use all of them. But as you can see here, there's quite a bit of information. And it also has a latitude, longitude that I think I converted. Let me see. Yeah, you can see it's all points. So I created, out of the lat long, I created this geography column over here. So let us now run some queries in SQL Server. So this first query here, I want to run a query to see which airports will be within a county. So I chosen my county here, Lake County in Illinois. And what I do is I create a variable to hold the geography object for that Lake County. And then I create a text variable so I can easily swap out the county I'm looking for, so I can try different counties. Here I'm querying from the Illinois County table that we imported from Census Bureau. So I'm getting whatever county I'm referring to. And then I have another table I'm querying from, the world airports. And from there, I'm filtering by the type is airport, because it could have been train and so forth. And I want the country to be United States. And then finally, I want to take the lat long points and I compare it to this polygon that I generated up here. And I want to find out which one of those airports fall within or touches on this Lake County polygon. And the way you do that is you say ST intersects, and then you place the polygon you're querying from up here. You put that inside the parentheses here, and you set it equal to 1 for true. So let's run this and see what happens. So I'm running. Okay, it finished. So now I'm looking at the results here, and it says 1,751 rows. Now I know for a fact there are very few airports in Lake County, maybe 1 or 2 or something like that, but not 1,751. So something is wrong here. So when I ran this query, I noticed this, and I was wondering, maybe my polygons are wrong or the geography is not correct. So then I started looking into this a little bit, and I discovered some stuff. So let me take you through what I saw. So the first thing I want to do is I want to make sure, in order to compare these, you want them to be the same projection. So we want them to be the WGS84. So what I do is I use this strid function, and I'm looking in the Illinois counties table, and I also look at the world airports table, and I'm trying to figure out from the geography columns that I created, are they both WGS, or is there a discrepancy? So when I run this, the first query will list all the counties, all 102, and it will give me the whatever the projection is, and 4326 is the WGS84. So that looks good. The second query has a lot more records, so I didn't want to include them all, but I can do this, for example, if you want to just see it and run it. And you can see 4326, 12,667 rows. So when I say I want to see where it's not that, I'll do it like this, and it doesn't find anything. So they're both WGS84. Okay, so what can be wrong then? I don't get it. So what I did was I went into the documentation, and I discovered this for the 2019 version. There's something called Reorient Object, because I guess SQL Server introduced something called full globe. And I try to look at this stuff, and because those type of queries have worked for me in the past, but now they suddenly return weird, strange result sets. And I took a look, and I printed out my long lat, made sure that the orientation was right. So what I ended up doing, and finally then, was to take this function here, like this, and I put it back into my query. So after I did these tests, I came in here, and I say, okay, I'm going to run this first without. So let me run it without. And you can see I'm getting my 1,751 rows. But once I put in this Reorient Object into my Illinois county here, notice what happens. I'm getting one record back, and that looks correct to me. There is Waukegan National Airport, which is in Lake County, so that looks correct. Just to test it out, let's also try another county. Let's try Cook County, which is where the city of Chicago is. And therefore, you should find airports like O'Hare and those type of airports. Maybe Midway. Let's take a look and see. So I'm going to run that. And sure enough, there's Midway, there's O'Hare, and these appears to be in Chicago. So, see, Chicago. So suddenly this query works fine now. If you have a newer version of SQL Server, you should be very aware of this thing, because this could really screw up your geography. And I noticed this by accident, actually, because I had some more filtering in this query that I took out. And then I realized, oh my goodness, that there's something terribly wrong here. So I want to make you aware of this query here, this new Reorient Object for full globe. So what if I want to figure out what's the distance from Oslo, the capital of Norway, to the White House in Washington, D.C. So I went ahead and I grabbed some lat longs from Google Map. So if I take this and I go to Google Map, so as you can see here, it gives me the projection here. When I click on this little link here, if I right click, I get these lat longs. So when I grab those, it will copy it and I can paste it into my SQL window. And likewise, I can do the same thing here from Oslo. So I can grab those two. And when I do, I'll put them inside here. First you do longitude, then latitude. And because Oslo is east of the prime meridian, if you remember that from my primer, my first video, you remember that anything east of the prime meridian's longitude would be positive. And the latitude, Oslo is in Norway, and Norway is above equator, so that would be positive latitude as well. And that's why both of these are positive here, you can see. And because the White House is in the U.S., and the U.S. is west of England, or the prime meridian, therefore the longitude becomes negative, and that's why you see it like this. So that's the latitude is 39 point whatever here. So what we can do now, we create an instance of each, and then we calculate the distance, and we round it a little bit, and we can do it in meters and we can also convert it into miles, because the conversions from meters to miles is that you divide it on 1609.344 will be the conversion ratio to convert it into miles. So when we run this now, it tells us that the distance in miles is about 3,867 miles. So that's how you can do a distance calculation. By the way, you could go to Google here and check your answer. Do a search like this: distance from Oslo to the White House in Washington, D.C. And if you look at it here, there's a converter here. It says that it's about 3,882 miles. The next one, we're going to look at the distance from the Navy Pier here in Chicago, which is this location here. So if we look at that, and I say, let's go one back here, and go, okay, so we ended up in the wrong spot because, let's see if we have to have the latitude first here, and then a comma maybe. Sometimes they project it differently. SQL Server do longitude first. So now you can see we're at Navy Pier here. So this is the latitude longitude position for Navy Pier. Okay, so what we want to do is we want to figure out the distance from Navy Piers in downtown Chicago, which, let me see if I can put it on the satellite so you get an idea what it looks like. So this is what Navy Pier looks like from the satellite image, downtown Chicago. And what we want to do is we want to figure out the distance to O'Hare Airport from Navy Pier, downtown Chicago. So what we can do again, we can show it in meters and in miles by doing this conversion. But as you can see, the distance from O'Hare to downtown Chicago is about 16, almost 17 miles. In this data set, the world airports, there's also the trains, where the train stations are. So very similar to the query we just ran. What we can do is we can figure out how many train stations are within a distance of 5 miles. So here you can see the distance to Navy Pier and which train stations are closer. So as you can see, this museum campus 11th Street station is 1.86 miles away from Navy Pier. So that's close to downtown, in other words. And then we get the Union Station downtown, which is 1.92 miles, and so forth. So you can run distance calculations like this directly in SQL Server. There's also this target data stores that I showed you. So again, what we can do, we can simply get the geography from the world airports, from O'Hare. So that will find the O'Hare lat long point. And then what we want to do is we want to calculate the distance here to each target store that is within a 5-mile radius. So remember, the 1609 meters is per 1 mile. So again, we put a buffer around the geography point so we can see it, and we put a 1,000-meter buffer so we can actually see it. And here we're just showing the distance in meters and in miles. So when we run this, you can see they're within 5 miles of O'Hare Airport. This makes sense because Mannheim is very close. So you can see it's only 2.14 miles away, so that makes sense. Irving Park Road, I'm not quite sure about this one, but it's about 4.5 miles away. So that's the target stores you can get right to from the airport if you wanted to. Okay, the next one here, we want to find all the zip codes that intersects or touches or are within Mason County, Illinois. Now the reason I want to do this is because I want to show you the differences in how these are developed. So here I'm doing the intersect, here's the within, and here's the touches. So first thing we want to do is we want to get the general shape of the Mason County. So if I run this and you look at the shape itself, you can see this is what it looks like. So that's the shape of the Mason County. Okay, the next thing I want to do is I will do intersect. So all these queries are the same except for the function I'm using. So you can see here I use the intersect function, here I use the within, and here I use the touches. And they all do a union all with the shapefile from the Mason County. So let's run this so we can see what it will look like. So I run this. And now when I go to the Geospatial tab, notice the differences. This is the county itself on the top here. This is the intersect. And as you can see here, if I put some names on there, and scroll in, you can see these are the zip codes, right? So here's the zip codes that intersects. That means it can fall outside the shape, but it intersects, it touches it somehow. And you can see that. This one is within only. So you can see here, only those zip codes that fits within this polygon is going to show up here. And that's the within. The third method here was the touches method. So if you look at this one, you can see only those that touches the outer polygon of Mason County will count. You can see these zip codes only touches on the outer portion. This falls within whole county, and these are inside and outside as long as they touch within this polygon shape. And that's the difference between the intersect, within, and touches. The next thing I wanted to look at is the ST difference and union aggregate functions. And in the QGIS, that was the difference function that basically finds the difference between two geospatial shapes. And the dissolve function is when we, well, I'll show you here in a second. So what I'm doing here is I create a geometry object called difference. I'm getting these counties from the counties table. So the county numbers I'm getting are all these are on the upper east side of Illinois, where the state is 17. So I'm just going to get these counties here, and then I'm going to aggregate them together into one shape. And then I'm going to get counties that are in the state of Illinois and aggregate those together again into one shape. So you get the whole. I could have just gotten the state file, but I wanted to show you can aggregate anything here into a bigger shape. So here I'm going to aggregate up to the state size. All the counties, 102 counties, are going to be basically created into one shape. Then I'm going to select this northeast geometry, consisting only of these counties. Then I'm going to collect all of the Illinois, the state, all the counties in the state. And then I'm going to look for the difference. Then I'm going to put it all together again. So when I run this query and I look at the output, go to spatial results. So this is those counties that I had queried first, these guys up here. It's in the one shapefile. You can see that top one here. And then the next one should be all the counties in Illinois merged into a state file. So that was 102 shapes here that was merged out, and only the outline is left when you use the union aggregate. The third one is when I find the difference. So basically it will be this piece minus this top corner piece up here, and that would be the difference file here. And then I put it together again, take the northeast and union with the difference file, and by running that query I basically put it together again, but it shows up as two shapes. So it's this one, that one, and it will be combined with this one. So that's how you can find the differences, and you can merge it together again into one shape. So that's what the union aggregate, the difference, are doing, which is equivalent to difference and dissolve in the QGIS. If you want to find out which inside this spatial reference system is not measured in meters, which type of projections, you can run this query here which says not equal to meters. The unit of measure is Clark's foot, Indian foot, German legal, foot, radian. So some of these are not measured in meters. When we use functions like simplify in QGIS, or which means the reduce function in SQL Server, the tolerance for these functions is in the unit of measure, which is meters. So here, for example, what I'm saying is I want to reduce the geography object by 5,000 meter tolerance. And if you remember, the reduce function uses this Douglas-Pucher method where you create smaller number of points. So what I'm doing here is I'm doing the original shapefiles from the Census Bureaus, and I'm finding the number of points in it. And then I'm running it again, but I'm reducing it this time by a tolerance of 5,000 meters for the whole state. And then I can compare the two. So that's what I'm going to run now. So when I run this, you can see that the original shapefile has 19,744 points, which is quite a bit. And if you're going to do that for every shape and try to put a report, the rendering will be slow. So that's why we try to reduce as much as possible sometimes. Notice I got it down to 56 points only by doing this. What does the difference look like? Well, let's make this up. And because it's geography, it's not very pretty, the display here in SQL Server. But let me try to bring it up a little closer here so you can compare the two. So if you look here, here's the original with all these zigzagging here. And here's the 56-point version of Illinois State. So the general shape is there, but as you can see here, it's greatly reduced the number of points here. You can see here is just like 4 points. Here's a bunch of points. So depending what you're looking for, the reduce might be your friend here if you want to have a smaller footprint in your reporting. To give you a visual of how this reduce works, I have a series of queries here. So let me just talk to this one here, and then I'll point out the differences in the next two queries. I basically create an integer, call it max row. I figure out how many points are in the Illinois state file that we get from the Census Bureau by using this stnumPoints. I load that in here. That would be the max number of points we're going to be looking for. Then I'm going to get the Illinois shapefile itself. By run this query, that will give the actual polygon. Then I create a temporary table called a point table that has two fields, row num and a point, which is geography type, and the row num is just an integer. And then I create a point variable of type geography. Then I create another variable, I set it equal to 1, which is going to be the counter I'm going to be using. And then I do a begin and an end statement. And inside there I have a while loop where I say, hey, as long as this current row is less than the total number of points in the Illinois shapefiles, then continue. And then what I do is I select into this geography variable, I grab the shapefile I have here, and I use the st point number, which basically you can find individual points in that shape. And I keep increment this current row. It starts at 1, so it looks for the first point here, and then as I increment through this, it goes second, third, fourth, fifth, and so on. And then I insert those values into this temporary table, and then I increment my counter, the current row counter. And then I keep repeating this. At the very end, I simply do a quick select statement, and I convert the point into text so you can actually see what it looks like. So let's run this query and see what it looks like. So this run for a little bit. So if you look here, there's 19,744 rows. And since I converted to text, you can actually see the long and lat points here inside this point text representation. So that's the first query. It has 19,744 rows. The next query is very similar. It only differs in that I load the shapefile as well in here. And then I'm doing all the points together with the shapefile, so it will overlay the shapefile itself. So this query is pretty much the same with that exception. So let me run that again. Now I'm showing not the point and text, but I'm just showing the geometry as a binary object. If you actually go in here, notice it can only display 7,599 objects out of the 19,745. So once it loads up a little bit here, it takes a while for it to render all this because there's so many points, and it gives you an indication of how much work there is to actually display this, the rendering for all these points. So here's what it looks like. If I keep scrolling in now and go to this shapefile, you start seeing along the border there's some gray stuff, and as I zoom in more and more, you can see how close every one of these points are. Each one of these little circle here is a point. So you can see there's a lot of points on this shapefile. So obviously that's going to take resources to load. So here in the last query, I'm actually using the reduce function. So what I do is, to find the max number of points, I use a tolerance of 5,000 meters. Because remember, the reduce for geography looks for a meter as the tolerance input here. And then I get the number of points. Likewise, I reduce the shapefile by 5,000 meters as well. Then I run through the same stuff as before. There's nothing new. And I do my final query here, and then I just get the state by itself so you can see what it looks like. So when I run this query now, you can see that it's going to run much faster. This time, it produced 58 rows. So when we look at this one now, this is what the geometry of that Illinois shapefile looks like. So if we make this a little smaller, and then we'll drill in here. So as I zoom in, notice you're going to start seeing much less points here. So I can put the name on here so you can see it. It's just a number because it's the row number. So when you look here, 2, 3, 4, and here is 54, 55, 56. So there's 58 rows in this shape here. Oh, there's 58 rows. Okay, but that's 56 points, I believe it was. If we scroll down here, we're starting at Illinois was null, so that represents a row too, that's why. So you can see here it's 56. And also notice that this point should be the same as the first point because it needs to enclose the polygon. And that's why you see this 56 and you don't see the 1 because 56 is overlaying the 1. That's how you can see the individual points, but a lot less points. It still looks like the shape of Illinois right there. So that's probably a very important point in showing you that in order to render some of these geography objects or geometry objects, the less points you need, the better, the faster it will render. Another thing we can do is we can try to find the center point of this Illinois shapefile. And in order to do that, notice I do two things. One, I'm grabbing the geometry object of Illinois, and then I use this stcentroid function to find the center point. But then I convert that geometry here by making it into geography, and I make it into the WGS84 SRID. So that will create this center point, and then I use my usual technique of union all the stuff here, where I get the geo name, the geography of the actual state of Illinois, and then the center point that I'm grabbing from up here, but I put a buffer on it so you can actually see it, and I make it really big here. I make it a 15,000 meters. So because it's a geography object, this would be in meters, as you recall. So if I run this now, and we look at the results in the Spatial tab, you can see here is the geography representation of the state of Illinois. And if I put the geo name on it, you can see that's the center point of the state of Illinois. Another thing we can do is to use a combination of putting a few states together and then do a union aggregate to see what the combined shape will look like by using this outer polygon ring, if you will. So what I'm doing here is I'm basically just filtering out 4 states, Illinois being one of them, and then I dissolve those 4 states into another shape here. So let's run this and see what it looks like. So if you open up this, you're getting the individual states here. We got Indiana, Illinois, Wisconsin, and Michigan. And those were the state FPs that I used to find those. And we got the geometry here, and then we got the geometry aggregate. So if you open it here, you can see, let me put the name on it. This is individual shapes for those 4. And on the bottom here, you can see this is the combined dissolved shape of those 4. Finally, I have one more nearest neighbor search query. So as you can see here, I have some different places. So what I do is I find a very popular tourist attraction around here where I live is the Great America. And that's located in this longitude, this latitude. And if you take these two and put it on a Google map, you're going to see this. So here you can see you're in a parking lot of Six Flags here. And there are all the rides and all the restaurants and stuff around Six Flags. So a lot of people who goes to Six Flags, they park here, but then they're looking because not all of them wants to eat inside the park because it's a lot more expensive. So they're looking for restaurants and stuff like that around the park. So one way we can do that is to say, what kind of fast food restaurants are close by the entrance of Great America? And then we might want to measure it in miles. Maybe we can set how many miles are we willing to go to find a restaurant. So the first thing we do is we load that geography object based on a point. So we use the st point from text, and then The fast food search area is going to be this, and then we're going to put a buffer around it, so a circle around it for 3 miles. So that will be the 3 times the 1609 meters, which is in a mile. And then I will simply create a with query, CTE, and then I run this query inside of it, where I use a filter in this case, and I filter by that buffered fast food search area. And then I select the top 10 from the results from this CTE here, order it by distance in meters. So when I run this whole thing, you can see this is what it will look like. So there's a McDonald's, there's a Burger King, and they're very close, and I know that for a fact because I know where they are. And as you can see, there's not even half a mile away. And then there's another one on Grand Avenue, and KFC, Taco Bell, and so forth. So you can use these kind of queries, and obviously you can show them too, like this, and put maybe, well actually we can put the actual name if we zoom in far enough. So here you can see there's a McDonald's. Those are the kind of nearest neighbor searches you can do as well. Finally, I want to look at a couple of queries that describes geography and different ways you can look at the geography and geometries of these objects. So I'm going to run through some final queries here to demonstrate this. First of all, against the world countries table, I'm just going to run a very basic query where I extract out the name of the country and the geometry, just so you can get familiar with it again. As you can see, this is what Hungary looks like. We can just quickly look at the name here, scroll in. So that's Hungary, okay? Next query I want to run is to figure out what kind of geometry type is Hungary. Is it a point? Is it a line string? What is it? And in order to do that, you can use this stGeometryType function. So I'm going to run the same query again, but now I'm going to look for the type. So when I run, you can see the shape of Hungary is a polygon. Okay, that's good to know. What kind of reference ID did we use to create this shapefile? And again, we've seen this before. The STSRID function will find which projection you're using. And as you can see, 4326, and as you know by now, that's WGS84. Moving on, this particular query will demonstrate Hungary as a shape object versus Alaska in the US. So in order to generate those shape files, what does it take? And here what I do is I figure out how many number of geometry objects are we using and what's the type, which we just did. So if I run this one for Hungary, you can see, well, it's a polygon, and we already looked at the shape. It looks like this. Now, when I run it against Alaska, and this time I'm just going to run both of them, so you can see Alaska has 50 objects that makes up the geometry of Alaska, and it's of type multi-polygon. So that means there's more than one polygon. So if I look at the spatial results, you can see this is one polygon here. And if I zoom in a little more towards Alaska, you can see every one of these little islands here is its own polygon. So it consists of, according to the results, 50 objects of 50 polygons. So in this case, it's a collection of polygons. Okay, moving on. So here I'm using I'm using convex hull. I'm using the envelope function. And then I do a basic normal one, so you can see them all together. So let's run that. When I bring that up into spatial results, you can see here is the square orange area you see here. That's the envelope. Okay, it's like a rectangular thing. So that's this portion of the query. The little darker orange you see here, that is basically doing the smallest possible enclosement of the polygon shape for Hungary here, is this little darker orange. So that would be the convex hull. So that would be this portion of the query. And finally, the actual object itself is that purple you see here. So you can combine these three so you can see how you can use either an envelope or convex hull to cover that polygon. You can also get the first latitude and longitude from a geometry or geography object. If I want to get it from a geometry object, then you can refer to this st.n function, n standing for a number. So if you want to find the first latitude, longitude in this shape, you set a 1 in here. If you want to find a second, you do a 2. If you want to find a third, you do a 3, and so on. And the last one, you might use some code to find it, or if you know the number, you can bring it out that way. But in this case, we're only looking for the first lat long. And because it's geometry, you can use this sty function or this stx function. So because x will be moving across here, and it will therefore be the vertical lines you're looking at, that would be the stx function. That would be the equivalent to a longitude. Sty would be from north to south, so that would be the latitude. So that's the sty, because remember, geometry is on a xy plane, okay? So if I run this, the first point, the first latitude, longitude for the geometry object is 46 latitude, something here, and 21 longitude for Hungary. And because Hungary is east of Britain, therefore the longitude would be positive, as you should know by now. Here is another query that expands on that same result set. What I'm going to do here is I'm going to find the number of points that you find in this polygon of Hungary. And so, in other words, it counts the number of points it uses to generate that polygon. And that's what I call the last point here, and I make it an integer. The first one will be a top 1 query. So I get the first point here. So I get the last point here. I get the first point here. And they're based on geography, as you can see. So I convert the geometry object to geography and I make it valid. I force it to be, make it valid. So it closes the polygon starting and ending point. Then I just write the final query where I do a union all as usual. I get the geography first point here as the latitude. And since it's geography now, you can take this and specify which latitude are you looking for. I'm looking for the first latitude here, and I can use this .lat function. That, as you recall, for the geometry object up here was the sty. Okay, so to find the same for geometry, use sty, stx. For geography, you use lat and long like this. So that will find the first point. And then I do a last point query here. How do I find the last point? Basically finding the number of points in that object will give me the last point. Then I can just put that integer in here, just much like I do here, 1, 2, 3, and here the last point will be whatever it is. Get the latitude and longitude here and run it. So let's run this query and see what we're getting. Now, if you remember right, what do you suspect it will be? Think for a second. Well, they should be the same. If they're not the same, then it's not a valid geography object, because the first point and the last point are basically starting and ending. So they should end up at the same point. So that's why you would expect these to be the same. So that was a little bit about how you can identify these different points. You can also inspect geometry types. I can find, for example, the number of points, which you saw before, the geometry type. I can also do is it valid for geography type. I can use this is valid function to find out. So let's just run this quick because you've seen most of this already. Probably haven't seen this is valid before. But as you can see, if I run this is valid, which is the second query you see down here, it comes back as a 1, meaning it's a valid geography object. You can also see for every one of these states how many objects they're made out of. In other words, in this case, how many polygons Alaska is made out of. As you already know, that's made up, I think it was 50. I don't think we have the count here. We have the number of points that goes into all this, but we don't have the actual individual polygons. So anyways, you can look at that there. And of course, if you try to display this, you're probably going to run into some issues because it's probably too many points to display. That would be my guess on the bottom one here. So let's see, it's running. And when it finally completes, yeah, you see some weird stuff down there. So I don't even want to continue with that one because it simply doesn't display very well. You can also find out by using the geometry object stEnvelope function. And from there, we can keep, remember this is a CLR object, so you can keep appending functions to it. And here what we do is we get the geometry object, we get the envelope of it, so it basically surrounds it with a rectangle around the object. Then we find the first point of the x-axis. Okay, so that will be the longitude, right? So the longitude we find by taking the min, that would be the most westward In other words, the left side of that rectangle. And then we continue around like that. If you take the min of the y, that means you're going to be on the bottom of that rectangle. That would be the most south point. And then you continue with east and north. So you can see that here by using this for geometry. Then what we can do, I'm looking for Hungary here, and I'm grouping by country. So in order to do this query, since I'm doing a group by here, I'm capturing for every, actually this is unnecessary, because here I'll filter by Hungary. Now I could take this at the where clause out and then group it by country. So if I want to do it, I can just comment this out, okay? Then what I do is I get the envelope, just so you can see the envelope. Then I'm getting the center point and I show it as text. Then I get the center point and I put a buffer around it of 10 meters. I'm sorry, whatever the unit is for geometry, in this case 10. And just so I can see what it will look like. It all depends, since keep in mind that the buffer in this case will be equivalent to probably 10 meters, because this geometry object was generated using like a world bounding box. I don't know if we remember that, where we said the geometry object for like a world map would be -180, 180, meaning longitude, and -90 South Pole to +90 North Pole. So it should be fairly equivalent to that 10 meter tolerance for the geography object here. And then I'm getting the 4 points from up here, from this CTE object, or the common table expression object, if you will. And I'm getting that from a combination of this table, which is these, and from this common table expression up here. Then I join it on the country field. So let's run this and see what happens. Okay, so now you can see the output. We got points, we got the envelope, and then we got for each object here. Remember, we took out the country. So this should be for every country. And you can see there's 252 rows. That's for 252 countries. You can find the westward point, and the south, east, and north. So if I put some of this in the spatial results, I could just filter by Hungary so you get a little smaller footprint here. Let's just run it again. Otherwise, it's too much to display. But you can do it either way. It's up to you. Here's just one row now, right? And here you can see the centroid point in text. So if I run this now and say centroid, this is the envelope. I can also just show the centroid like this. It's not very clear when you look at it. I would have to probably unite it with the actual shape and so forth. So I'm just showing you these different functions you can run so you can play around with it yourself. I'm going to skip this because we already talked about these centroids and all that stuff. And it's just, I don't want to rehash too much. I'll show you the query for a second or two and you can look at it. And if you need to do something with it, you can just read it from here. Okay, so one thing I want to point out though, that particular query I showed for Hungary up there, that's for a polygon. Now if you want to see for United States, okay, United States has the continental United States, which is the kind of shape you're most familiar with. Then you have Alaska, and then you have Hawaii. So what happens here, when you try to find a center point, where you filter by United States, and you get it from the geometry object, you get the centroid from the geometry object, you convert it into geography, make it into WGS84, and then you find that center point. And when you combine that with the actual shape now, I'm just going to run this query, you can see United States is a multi-polygon. And here is the shape of United States, and here's the center point, and I made a buffer on it. So if you look now, and I scroll in a little bit, and I put up this country, notice what happens. United States is this continental portion, Alaska portion, and down here, as you can see, is Hawaii down here. So what happens, to find the center point from different polygons like this, it will basically outline all of these guys and try to find the center point. So you see it's moved towards the northwest position, the center point. It's not in the center of the continental USA, it's in the center of all these shapes. So you're going to see that when you're actually calculating center points. The final query I want to do, I want to show you how you can do an area calculation as well. We can calculate the area of, let's say, Germany. And we basically take the geography area here and use this area function and then do some calculation. Because when you do area, you're getting in a metric system, you're getting into square meters. Because remember, the WGS84 is in meters. So when to convert into square meters, you got to do conversions. So in this case, for kilometers, there is 1,000 meters in 1 kilometer, okay? So in order to find out how many kilometers those meters are representing, you divide it by this factor. And then I'm simply rounding it by 2 here. For miles, this is the factor you need to multiply by. And then here I'm getting the geometry object. Here I'm getting the geography area like this. So that's going to be in square meters in this case, because I'm not converting it. So let's see what happens. So I'm going to run that. And as you can see, the area is in meters, this is in kilometers, and this would be in square miles. And the actual shape of Germany looks something like this. And what you can do is you can go here for this link, and you can Google it and get approximately how large Germany is. And it's off by a little bit, but it all depends on how you measure it. That it will look something like this. And if you compare the area of Germany with the area that we computed using this factor here, you can see, so this is in square miles. So it's very close. It all it could be slightly off with lat longs, what have you, in that world map table. So anyways, that should give you an idea of how to do these calculations.